Once again, good morning, everyone. We'll
Good morning, sir.
morning and we'll start with our class today. So we will continue with what was left from the previous class. So last class, if you remember, uh, we saw some of the input-output devices and some sensors and actuators, right? Like typically we saw about LED, your relay, and also push button and also optocouplers. So we'll again see a few more that are left out in the same area. Okay, the first one in this is stepper motor. Okay, so a stepper motor is actually a variant of a normal DC motor. So a DC motor is the normal motor that we all are aware, right? When you give a DC electrical signal, it's going to start spinning, right? So there's going to be a rotary motion. However, in a stepper motor, it still is going to do a rotary motion, but it's in a very controlled fashion. Okay, so very controlled, discrete steps of rotary motion. Okay, so that's what a stepper motor is. So the definition goes like this: stepper motor is an electromechanical device which generates discrete displacement. This is the rotary displacement in response to a DC electrical signal. uh, so this is again different from the normal DC motor. Normal DC motor, as soon as you supply the DC voltage, starts spinning. Okay, you just count the RPMs in the normal DC motor. However, in a stepper motor, it's the number of steps. Okay, so that's how it works. So it's widely used in all the industrial applications. So if you take a simple example of a printer or a fax machine, right? So the paper feed mechanism, the way it takes in the paper, it's actually controlled through stepper motor. You would have seen how discreetly the paper is fed. It's not like a continuous movement, right? It takes the paper in steps. So that's where the application of stepper motor lies. So based on the coil winding arrangements, right? Stepper motor can be classified as either unipolar or a bipolar. Okay. Just give me a second. So let's take an example, right, of this unipolar bipolar windings. So the figure on the left shows a unipolar stepper motor. So it's called unipolar because so with one switch you can actually control all the poles. So in some essence there is only one pole that is in control. Okay, so how it works is there are two windings here, as you can you can see the two windings. In that uh, there is a common winding here. Okay, so there's a common wire that is shared between the two different windings. Okay, so which means that if this is supplied with positive plus V voltage, the remaining ones can only be either grounded or yeah, that's the only option, or it can be open. So that's the only option. Okay, so that is how the unipolar stepper motor works. On the other hand, bipolar stepper motor, it it has individual control. Okay, so each of the winding, you can choose what uh, voltage it has to take. Okay, similar to this particular winding here, there is also one more winding that will be here in this in this coil, and then you can control this independently of this. Okay, so it gives you more flexibility in terms of, or you can independently supply the voltage. Okay, so that's the difference between this unipolar and bipolar stepper motors. And in this in your syllabus, we are only dealing with something called as a two phase. Okay, two phase stepper motor, where it's simply it's something like this. So you have only your stepper motor has only four half steps, like it's either on the top or on the right or the bottom or on the left. So only four, right? So which means like there is only it's like a plus symbol, isn't it? So that's why it's called as a two phase. So this is one phase and this is the other phase. On the other hand, there are also five phase stepper motors where you will have like one and then two, three, four, five. So you will have that many number of these coils. Okay, so but for our learning purpose, here we will only see two-phase stepper motors. Any questions so far? You guys can hear me, right? Hello?
Yes, sir, you are audible.
Okay. Let's quickly go over a comparison between unipolar and bipolar. So unipolar stepper motor always energize the phase in the same way, like we saw, right? So there was one common lead that will always be negative, or it can also be positive. So that's always given a particular voltage. So it's either positive or negative depending on which way you want the motor to rotate. Okay, so it's a common lead, but on the bipolar there's no common lead, so all the phases are controlled independently of the other. So because of this common lead in unipolar motors, so with one supply voltage, right, it has to share among the two different uh, uh, phases. So because of that, you have less torque. So torque is nothing but how much force, the angular force, right, is called torque. So how much angular force that the motor can pull or push, right? So how much it can give. Like for example, to give you an example, if you tie a particular weight to this stepper motor, right? So how much weight that the stepper motor can pull, so that gives you like an idea of what a torque is. If you take unipolar motor, it cannot pull that much or push that much, so it's like it has a less torque because the supply voltage is shared. But in the bipolar you have independent supply voltages, and due to this it has more torque. Okay, and each has its own advantage disadvantages, and one of the advantage about unipolar is it's cheaper and it's easier to implement. It's very simple implementation, as you saw, with one switch, right? Or which means like one transistor you can control both the poles, while in sorry, not both the poles, both the phases. And in bipolar it's more pricier and it's more involved in implementation. Okay, so so I'm going to share this video to you. So when you have some time, you can look into this in detail. Okay. So but what I've done is we've taken snapshots of this same video and explain this to you, so that it'll be easier, because the figures in the textbook is not that clear. Okay, so anyway, to go with the unipolar, right? So this is how it works. So as you see, there are four different coils. So A, B, C, and D. And so this particular wires you see, right? So it's actually a common lead. Similarly, this is also a common lead. So both, so this common line and this common line are both tied to ground, or to a supply voltage. So depending on how it spins. Okay, and this is how the clockwise or anti-clockwise motion is achieved. So first step is you supply the current. So and another point here is the unipolar stepper motor works based on how you the direction and the amount of current supplied. With the amount of current supplied and also the direction of current supplied, the each of the windings are going to get the magnetic field accordingly. Okay, so in first step, what you will do is you will actually supply, you'll make sure the current moves in this clockwise direction in this particular winding. Okay, so which is nothing but your coil D, right? and it gives this north and this south. So this will be the magnetic field, and because of that, the magnetized part of the motor, right? So unlike poles attract, so it goes by that principle. So it takes this particular state. Okay, so where you have south here and then the north here. So this is the state of your motor. Okay, actually the rotor of the motor. Now, so the second step, what you will do is you will switch the current to the winding B. Okay, in winding B, you will pick the clockwise current. So when you take clockwise current in winding B, particularly the coil C, what happens is now, so it charges the same way. So so this becomes north, this becomes south for this particular winding, and then now the motor, if you see the rotor, it has taken the state from this, your south has moved from your right side to the bottom. Okay, similarly you can change the state next to the other, again back to winding A, but now the current will flow in the anti-clockwise direction, and again following this winding B again, and then anti-clockwise direction. So when you do this particular thing, so you actually complete a full cycle, as you can see. So this is moving the rotor in clockwise direction. Okay, and then still clockwise, and then it has completed one full cycle. Any questions? Okay.
No, sir.
Okay. Yeah. So now there are different modes of operations based on how you energize the coils. Now imagine this is the stepper motor, right? So you can do something like this. It's something called as a full step mode. Okay, where you will actually go one full step. So what is one full step here? It's 90 degrees, right? So 90 degrees is your one full step. Let us assume that initially you're charging A and B with the same poles. Okay, so if A is north, B is also north. Okay, so what happens is the south side of the coil, south side of the rotor, right, the magnet is going to attract it equally to both A and B. So it is going to take this middle position. Okay, it's going to point in this way. Correct. See, previously what had happened, if you see here, right? So in this particular state, you are only giving the field to one of the windings. Okay, because of this, what's happening? It takes either it points to the top or the right. Okay, but here in this mode, you're giving north, you're charging both the windings at the same time. So the magnet is in between A and B. Next, what you will do is you will switch the charges to B and C now. Okay, so you take a 90-degree turn from this state. You take a 90-degree turn, it goes to this, right? So okay, so this is your initial state. Okay, and then the 90-degree will be this. Okay, so it's going to be something like this, and the next step is going to be this 90 degrees. Okay, so at any given step is going to be a 90-degree rotation from your previous state. So that's why it's called as a full step mode. Okay, you take a full step. And how you charge it? So it's like this, right? Coil A and B will be charged first, and then you'll energize coil B and C, and then C and D, and then D and A. Okay, so with this you have completed one full motion in steps of halves. Okay, so sorry, in full step. Sorry, full step. Okay, everything is a full step here. Now there's one more possibility, right? So instead of charging two, so like we did in our first slide, so you can just charge one winding at a time. Okay, so that is also possible. That is also called as a full step, but it's termed especially, it's also called as a wave step. Okay, so here what happens is you charge only one coil at a time. So A will be charged first, then you take a 90-degree turn. Okay, so then B will be charged next, and then your C. So this is 1, this is 2, this is 3, and then this is 4. Okay, and then you go down, and then you go here. So you complete one full motion. Okay, so one full rotation. Any questions so far? So both these are full steps. Okay, one full step in a uh, two phase stepper motor is actually 90 degrees. Okay, so 90 degrees is your full step. Any questions? Are you guys understanding, you guys?
Yes, sir, we are understanding.
Okay, next we'll see half step and micro stepping. Okay, so now you got the idea, right? How to play around with these different coils, how to energize them, and then you can actually control the magnet movement. Okay, so like you see here, so you will now go in half steps. So first you will go for this wave step. Okay, so you will charge only one of the winding. So then what you'll do is you will charge A and B simultaneously. Okay, so then what happens, so if this is also charged, so then your magnet will not move all the way to B, because A is also charging, B is also charging, both are say north north. So then the south of this is going to occupy the middle position. So initially this was north and this is south, right? So this is how the initial position is. But the next time when you're charging both A and B with the same poles, so it's going to occupy this 45-degree position. Okay, so this is 45 degrees. Okay, okay, so then what you will do, you will remove the charge from A, but B will continue to get charged. So then from this position it will go another 45 degrees, and then it will take this position. And now you know you how you can play around, right? So now this, you're not going a full step. No, you're not going 90 degree at a time, but rather only half steps, which is 45 degrees at a time. So for this reason it's called as half step. There is also something called as micro stepping. So remember I had mentioned to you that uh, the unipolar motor works based on your current supplied. So now what you can do is you can actually alter the current. So let us say you're giving a current of say 5 milliamps or something like that, and then you can give a current of 10 milliamps here. Okay, so which means that this will this particular magnet is going to get the north here, and both are north here, and then this is south. But the north here is more attractive, or it has more magnetic field than the north in this particular coil, right? So because of this, this magnet is going to move ideally, if it is both are 10 milliamps, it's going to occupy the 45-degree position. But now this is 5 and this is 10, so it's going to take a position somewhere here. Okay, because B has more pull than A. Okay, so with this you can control not only full steps and half step, but also anything in between based on the current you are supplying. Okay, so this is called as micro stepping. So you can initially give A as 10. So initially if you give A as 10, and this is 0, then it will be at this place. Then what you can do is you can give A as 10, and then B also as 10, not 10, sorry, B as 5. Then it will occupy somewhere here, because A has more pull, but B is also pulling slightly. Then you will make both A and B as 10 10. So then it will occupy 45 degrees. Okay, so then what you will do, you will actually make A as 5 and B as 10, so it will occupy somewhere here. And finally you will make A as 0 and B as just 10, so it will occupy. So you see it will take 45 by 2 degrees. So that's how you can control this, right? So you can even go at you can even divide it into further micro steps. You understood this part? Any questions, guys?
No, sir.
And next, we'll just quickly see how it is interfaced. Uh, so basically, you have your microcontroller, all the port pins coming out from your microcontroller, and you also have a driver circuit here. So what the driver circuit does is it gives the intelligence. So we saw earlier, right? So initially, what are the windings that needs to be applied the charge and how the current should flow. So based on either a diode or even a transistor sometimes, right? So you actually control this particular circuit. So if you remember, there was one switch that used to control the which windings should be connected. So the driver circuit takes care of that. Okay. All right. So that's pretty much about the stepper motor. Any questions, guys? If not, we'll move on. Relay, we've already seen it in the previous class. Just to give like a very brief summary of that, relay is again uh, is a switch controlled by a magnetic field through a coil. Okay, so there's a relay coil. So based on how this is charged, it's going to either leave the switch open or it's going to close the switch. Okay, so that's what it is. So we already saw this earlier, so we're going to skip this further. Next one is piezo buzzer. So it's a piezo electric device. Okay, so which means that it's going to have like a mechanical motion when you supply electricity, and so this particular buzzer is going to produce a noise or a sound, a buzzing sound with a particular tone. Okay, so based on the pulse that you give, these buzzers can produce different uh, uh, notes of sound. Okay, so let's just one second. Yeah, so that's pretty much about this. Okay, so you need like an external driver similar to other sensors or actuators. You need to have a driver that supports this, and so you can interface it with any of the port pins. Okay, it's a very simple concept. And then we have push buttons. We already saw about these push buttons in the earlier class. So basically, these are the buttons that we see on our boards, right? The GPIO pins, all these things are connected to. I mean, all these are actually connected to push buttons. So here, if you have, so there are two types. As we saw, push to make and push to break. It's something like this. So push to make. So it's this one. So when initially it'll be the port pin is grounded. Okay. So but if you want to make a contact, you push the button. So then the path of least resistance is picked. Okay, and but push to break is a little different. So here you always connect it to the supply voltage, and if you push the button, it will take the path of least resistance and it will get grounded. Okay, so this is the difference between these two, and again we saw this in the earlier class. Next we move on to keyboards. Okay, keyboard, also known as matrix keyboard, is an input device used for user interfacing. So this is nothing but like array of these push buttons. If you think about it, let's I mean our standard keyboard has 110 keys, right? So think of this as 110 push buttons. So that's all it is. However, so it does have some internal logic, and why is that? Is because you still don't use 110 ports, right? 110 or 220 ports. So we don't use that many ports or pins. Okay, we still connect it through either com. We used to connect it through com ports, but now we are connecting it through USB ports. So that's the difference, right? So it's an enhancement to the push button concept. where all of these multiple switches are still connected through one port. Okay, so that's the logic behind it. So you use an internal logic to simplify this interfacing. And so the matrix keyboard has rows and columns. As the name indicates, it should have rows and columns. And there's also something called as a debouncing, which needs to be implemented either in hardware or software. Okay, so we'll quickly see this in the next slide. So the keyboard, as you see, so this is the interfacing for this keyboard. Okay, so you have your port 1 and port 2. So this is your input, and then you have the output. So these are the different push buttons. Okay, and so here you have uh, the supply voltages. It's pulled up with pull up resistors to VCC, and based on which switch you push, so you are going to get that circuit shorted, and that key is going to get activated. So it's as simple as that. Okay, so that's how the keyboard matrix is designed. Okay, it's similar to, if you think about it, if you have seen this PLA or PLCs, right, earlier. So that used to have a similar kind of circuit. So where you have rows and columns, and if you want to select a particular line, so you want to select this particular key. Oops, sorry. It's going to, you're just going to short that particular line. We were also talking about debouncing, right? So if you think about your keyboards at a human level, so you're just going to push a particular key. Let us say you're going to push down key A. Okay, so you think that you're pushing the key like this. So you have a push button. Okay, you have the key button here. So the moment you push it, it's supposed to go from here to here, right? So that's how you are expecting the behavior to be. But in reality, that is not the case, because humans are uh, first of all not very accurate, and the second thing is so the keyboard is actually like an electromechanical device. So there is a mechanical motion involved here. It's not simply electrical, right? So because of this mechanical motion too, so there is going to be some kind of a glitch. So you are actually not pushing it like this, but rather you will be pushing the button something like this. Okay, so when you push the button, so at a very micro second level, there is going to be some bouncing happening. Okay, you think that you've just pushed it, and it should just go from 1 to 0, but it won't happen. So it will be something like this. The moment this is where you actually start pushing the button. So then you go all the way down, and then there's going to be some bouncing, and then now imagine you're pushing the key A. Then what you are supposed to see in the monitor is A, right? But what you will typically see based on this based on this pulse is a. Okay, so how many times it has bounced, you will see that many A's. That will become a problem. So to overcome this, so there is something called, this is the bouncing effect. Okay, now because of the bouncing effect, you will think you just want one A to be pushed. Okay, but rather multiple A's will be counted. So to overcome this, you will incorporate this debouncing mechanism. This debouncing mechanism, as we saw in the earlier slide, it can be either a hardware circuit or a software circuit. So not software circuit, software mechanism. Okay, so a hardware circuit will take care of it in a hardware level, and the software mechanism will actually try to see the time, and then based on the time, it will interpret this as a single A. Okay, so every time you push a button in your keyboard and you see only one character appearing, you should thank the debouncing mechanism to have handled it well. Okay, all right, any questions, guys? Was it clear?
Yes, sir.
Okay, next we will see PPI. also called as programmable peripheral interface. Okay, so a programmable peripheral interface is actually a very interesting thing. So it's not like any of the other IO devices that we saw. So previously, that so far whatever we've seen, the sensor, actuator, or the IO devices, they interact with the user, right? They are either an input device or an output device. Okay, and then they directly interact with the user. But PPIs, on the other hand, it enables the processor or controller to have an extended I/O capability. Okay. In other words, if your microcontroller, right, it has only one port, one I/O port, then you can connect it to a PPI, and then you will have multiple ports. Okay. So you can have multiple ports using this PPI. So it's only like it's like an extend, it'll extend the capability. So you will do a multiplexing of the same IO port here, uh, and your PPI takes care of it, and your read write everything will be directed to this the ports A, B, C appropriately. Okay, based the microcontroller should also know, should be aware of this. The user should be aware, like user meaning the drivers, right, should be aware of where it has to be written. But nonetheless, you can still can multiply the number of ports that are connected to your microcontroller. So 8255A is a popular PPI device. So that's what we will be seeing for this course. So it's an 8-bit processor controller. That's what it supports. Okay. It has 24 IO pins and grouped as here, as mentioned below. Okay. So the 24 IO pins. So individual 24 IO pins will be grouped together in groups of 3. Say it will be like 8 parallel ports. Okay. Wow. Why did D come here? Sorry about the typo. Okay. So it's just ABC. So you have only 3 8-bit ports. It's port A, B, and C. Okay. And the other option is you can have only 2 ports, A and B, and the port C will be configured as like individual IO pin. Okay. So you'll have your port A and B as 8-bit port, but C will be like 8 individual IO pins. The other configuration for port C is it will be treated as 4 I'm sorry, 2 4-bit ports. It's called as C upper and then C lower, CL and CU, right? C upper is CU, and then C lower is CL. Okay, so you will treat it as 2 different 4-bit ports. Okay, and this configuration is done by a control register. Clear? So basically this 8255, the 24 pins control the ports A, B, and C. So each A, B, and C is 8-bit. It has 8 pins. So these 8 pins, the first 8 pins will be treated as like one port for A, and then the other will be like for B. But for C, it can be treated as either an 8-bit port similar to A and B, or it can be like all 1 bit pins, or it can be 2 4-bit ports. Okay, any questions? So as I said, you can uh, control, or you can actually configure these ports based on this control word, right? So here's what you can do. So initially, if you take so this is the control word. It's 8-bit again. It goes from D0 all the way to D7. So this control word. D0, the least significant bit, right? So it's going to specify how your port C is configured. So whether the port C is going to behave like an input port or an output port. Similarly, D1 is going to specify for port B. Okay, and here D4 is going to specify for port A. Okay, so Then you also have this D2 here, right? So D2 you have something called as a mode selection, and this is mode selection for CL. Okay, assuming that you are going to take CL, you're going to select CL mode. So then you have two different modes here. So either it will be 0 or 1. So 0 means port B will be 8-bit IO port, okay, and then port CL will act as a 4-bit port, like we saw earlier, right? So CL will be like a 4-bit port. But on the other hand, port B can choose to use some kind of a handshake. So what you will do is you will not use port CL as a 4-bit port, but rather that 3 bits out of the 4 will be used by port B for some handshake. Okay, so port B will use these 3 bits for handshake. So so this bit D2 is going to specify that. Okay, any questions on this? Hello guys. Hey, can you guys hear me?
Yes, sir.
Okay. Then we have your D3 where you say whether port C is going to be input or output device, similar to the other, so D1 and D4, right? And then you have your D5, D6 bits. So this is mode selection for port A. Okay, so this is mode selection for port CL and port B. So whatever we saw for D2, right? And here it's going to be mode selection for CU, and CU is your port C upper and port A. Mode 0 and mode 1 are similar to what we have seen here. It's going to be a simple IO mode, or it's going to be a handshake mode where port A will use the 3 bits from port C for handshake. And there is also one additional mode. So in mode 2, what happens is your port A will function as a bidirectional port. Okay, so you can configure port A as a bidirectional. Otherwise, it's either it'll be in like an input mode or an output mode. Okay, one of those. At a time, it can only be unidirectional. And finally, you have your D7, where you can specify the IO mode. This is for port C. Okay, so you're going to specify for port C whether it is going to be an IO mode or not. Okay, if it's IO mode, it will be treated as like your port A or port B. But then if it is in BSR mode, this particular mode will specify whether to do, it's called BSR, means bit set or reset. Okay, it's bit set or reset. So for port C alone, what you can do is you can reset or set the bits individually. Okay, so in order to enable that, you have this BSR mode. Otherwise, if it's one, it will be treated as a normal IO mode. Okay, any questions, guys? So to give you a big picture, so this particular control word, right? So you can configure the 3 ports, port A, port B, port C, in the way it has as the specification allows, right? So you can configure it in different ways for your own use. Now I've just taken this particular figure from your textbook because there are multiple ways you can interface this your PPI with microcontroller. So one way to do it is specified in your textbook. So what you have, the idea is this, right? So you have your data bus here, and then your address bus goes here. Okay, and you have a latch, and then with the latch you can select the particular pins here. So this A0 and A1 pin is going to select whether it's going to be how you're going to do the read and write. So it's going to be read, write, or is it going to be a reset. Okay, so and then your A2 to A7, which is pulled again from your D0 to C7, so the data bus. So here you're going to sorry, this particular A0 A1 is going to select which port you are directing it to. Okay, so it's going to say whether it's going to be port A, port B, or port C. And the A2 to A7, you'll go feed it through the address decoder along with the address bus, and it's going to specify the address. Okay, address of whichever location of the device that you want to write to. Okay, and the data bus, as the name specifies, it will give you the data. Okay, now in addition to that, you have this CS is called as chip select. Okay, so based on chip select, you will either turn on or off this 8255 chip. So you can actually say, okay, if chip select is not enabled, so then you will not use this. It means that you will just ignore all these signals. Okay, it's as if this has switched off. Okay, otherwise you will continue its functioning. So other than that, you have your read, write, and then reset pins here. Okay, it's going to specify what you are going to do. So as you see, there is only like one data port and address port coming out of your microcontroller. However, if you see outside of this PPI, right, so 8255A, so you're going to see three. Okay, you're going to have port A, port B, port C. Okay, so one typical example or a popular example for this 8255C is the traffic light. Okay, so you see in traffic light you have three different signals, right? Your red, and then your yellow or orange, and then you have your green, right? So but then your microcontroller will only have one port coming out of it, because it's going to be a very simple microcontroller you're going to use for traffic lights. Now you're going to use this 8255C, and then you're going to have three ports here. Okay, it's going to be port A, port B, and port C. So you're going to say, okay, now port A lights on, port B lights on, port C lights on. So you're going to control it using 8255 uh, uh, chip. Okay, so basically what you'll do is with one port, you're multiplying it into three different ports. You're extending the IO capability. Any questions, guys? Hope it's clear. So I would like to actually stop the lecture here. Okay, so we will see the communication interface. We've already seen like an overview in the last class. Okay, but we will continue the individual protocols in the next class. Okay, so far any questions, guys? Okay, so you guys can yeah, you're already doing it, right? You can copy the yeah, you can, yeah, type your USMs. All right, so let me go ahead and stop the presentation.